let's draw some pictures which compare improper integrals, the integral from a to infinity of f of x, and series n equals some number n up to infinity of a sub n. And when we're comparing them, we're going to assume that the function and the sequence have similar graphs. Basically, we're going to say they're compatible. F of n equals a sub n. The other requirements we're going to throw in here are that f of x and therefore a sub n is continuous. Well, only functions can be continuous. But the other properties will be given to a sub n, which are positive and decreasing. All right, so a sub n is positive and decreasing. It doesn't make any sense to say it's continuous. Okay, and let's compare the two pictures here. So if we have, and I'll draw the function in blue. So maybe it looks something like this. Make sure it passes the vertical line test. Okay, and I'll draw the sequence in red. So here are the points of the sequence. All right, and we're kind of just assuming that n is 1 and a is 1 in this picture, although it really doesn't matter for our purposes. Let me make a copy of this real quick because I'm going to draw two different pictures. So, all right, so now we've got two pictures. And I'm going to draw the area from a equals, we'll assume a equals 1 in this picture. All right, so if a is equal to 1, then from 1 out to infinity we get this picture. And we get the same picture over here. So same picture in both. Now how would I represent the series in these pictures? Well, remember, we're adding up just the numbers, a sub n. All right, here's a1, a2, a3, a4. And what I can do is I can draw, I'll do this in a lighter red, sort of a pink. All right, and what would this picture look like? I could draw it two ways. Over here I'm going to draw it like so. I'm going to draw it by taking the number up here, go out to the right and down. Here's the height of this would be a sub 1, the width would be 1, and of course 1 times a sub 1 is a sub 1. Here's a sub 2 times 1. Here's a3 times 1. Here's a4 times 1. And what I want to point out is that this area is bigger. All right, so this series is bigger than the proper integral. Okay, but there's another way I could draw the picture of this series as well. All right, first things first, we could just draw it to the left. However, I'm not going to fill this in because it is finite. All right, whatever it is, it's finite. And now I'm going to draw to the left the rest of these. Okay, and so if we look at it this way, other than a finite difference, the integral, the area of the improper integral is bigger than or equal to the series. All right, so if you're less than or equal to and you're greater than or equal to, then you're equal, except for a finite difference. All right, I did wave my hands a little bit because of this finite difference right here. So they're almost equal to each other. So I could put that equal star maybe. what does this mean for us? Okay, well, what it means is that since this area and this value only have a finite difference, that tells us that we're going to have shared convergence or shared divergence. Of course, if this blue stuff is infinite, then the bigger pink stuff is also going to be infinite. But if the light blue stuff is finite, then the smaller pink stuff is also finite. And that's the integral test in a nutshell. All right, here. If you got a function, f of x is continuous, positive and decreasing, and you have a sequence, a sub n, a sequence formula, which is equal to the function at the integers n, then the improper integral and the series either both converge or they both diverge. They match. So, if I want to know about the convergence of a series, I could test that by just taking the convergence or the divergence of the improper integral. All right, let's see this in practice. Okay. Does this series converge or diverge? All right. And there's possibly, clever ways we could reindex this to get a piece series out of it, but excuse me, we haven't learned what a piece series is. All right, so we don't know how to do the piece series yet. We don't have any way of knowing whether this converges or diverges. The series divergence test fails to tell us anything because the limit, the first thing I might try, the limit as n goes to infinity, 4n plus 4 over n squared plus 2n plus 1 is equal to 0. You can factor out n squared to see that. The problem is that it has to not equal 0 in order to tell us it diverges. Since it equals zeros, it's inconclusive. So that doesn't help us with anything. Series divergence test fails. But that's okay, because what I can do is just check the integral and replace all the n's with x's. And I could choose whatever a value I want here. I'll choose a 0 as part of the domain. I can plug in 0 on the bottom, so I'll pick that because it's easy. It does not have to match the 4 because that's not going to affect convergence or divergence, some finite amount of difference, right? Okay, so to actually do this integral, well, the first thing I have to do is change the top to a b because infinity is not a real number. That doesn't make any sense to leave it as it is. Okay, so now how am I going to integrate that? Oh, well, maybe I could try just a simple substitution. If I let u equal the denominator, my du would equal 2x plus 2 dx. Oh, but I have 4x plus 4 dx up here, don't I? So I can make that 2 du is 4x plus 4 dx. Perfect. So, oh, but then my x values are now u values, so let's make those changes. If x is equal to b on the top, then my u is going to be b squared plus 2b plus 1, whatever that is. And then my x is equal to 0 on the bottom. That gets me 0 plus 0 plus 1 for u. So 1. So we'll make those replacements. B is still going to infinity. On the bottom, my 0 became a 1. On the top, my b became a b squared plus 2b plus 1. All right, let's see what else needs to change here. The 4x plus 4 dx becomes 2 du, and the denominator becomes just a u. All right, so we'll integrate to get 2 natural log absolute value u from 1 to that bunch of b stuff up there on top. And then we'll plug in the top. And this is actually always positive, so I don't have to worry about absolute values. Minus, plug in the bottom, 2 natural log of 1. That's a big fat 0. But what's more important is what is the value of this right here. And, well, we have b going to infinity, so we have infinity plus 1. We think of this as infinite. Natural log of infinity, natural log is an increasing function. This is infinite as well. This is going to diverge. Okay, that's good news. So at the end of the day, what happened? Well, I did a seemingly unrelated problem about integration, but the integral test tells me that if I take the improper integral, I figure out that it diverges. Well then, by the integral test, I do need to write this so that the person reading knows what's going on. I'm using the integral test here. The series also diverges. All right. If I'd found out that this was a number and it converged, then I would say the series also converges. But this is definitely the series also diverges. All right, and that wraps up that problem. Here's another example. So what are we going to do? We're going to turn this into an integral. This looks like something I can integrate, maybe. Let's see. So it's not equal to the series, but I could take the integral from, let's just do 1. I could have used 0 or whatever else to infinity, and replace my k's, my index, with x's. X over e to the x squared dx. All right, and then I have to get rid of that infinity on the top, make that a b. All right, so let's see, what do I do from here? I need to let u equal x squared, I think. If I do that, then du is 2x dx. I have an x dx up here, so I'll make that a 1/2 du. It's x dx. And that changes my bounds a little bit. If x is equal to b on the top, that changes u is equal to b squared. If x is equal to 1 on the bottom here, then u is equal to 1 squared is 1. So I get the limit b to infinity from 1 to b squared. X dx becomes 1/2 du, 1/2 over, that's e to the u. Okay. How do I integrate that? I don't think it's written in a nice form. I think it'll be a little bit easier if I look at it as b to infinity 1/2 e to the negative u du from 1 to b squared. All right, so to integrate this, because of that negative there, we could use substitution again, or I could go back here and make my life even easier. In fact, I think I'm going to do that. I don't want that negative u there. I want to have a positive u, which means I need this to be a negative u. So I need negative u to equal x squared. So I'm going back here and I'm just fixing things a little bit to make my life a little bit easier. Negative u equals x squared. That means negative du is 2x dx and negative 1/2 du is x dx. What else changes here? I get negatives for negative b squared and negative 1. So let me fix everything then. So my bounds of integration became negatives. All right. I wanted e to the negative u. My x squared gets replaced with a negative u. That's fine. But then my x dx got replaced with a negative 1/2 du. Okay, so that means when I simplify this, the e to the negative u comes up to be e to the positive u. I still have that negative though. These bounds are still negative, but that's all fine. Because now I have just e to the u to u, that integrates to get itself. Negative 1/2 e to the u from negative 1 to negative b squared. Limit as b goes to infinity. And plug in the top. B goes to infinity. Negative 1/2 e to the negative b squared minus a negative 1/2 e to the negative 1. Okay, so let's see. B's going to infinity. I can rewrite this if it helps. I can rewrite that as 1 over 2e to the b squared. Limit as b goes to infinity. And the point is that this is going to infinity, so the denominator is going to infinity, which means that the whole fraction vanishes to nothing, vanishes to 0. All right, back over here, that's 1 over 2e, so 1 over 2e, that gets me 1 over 2e for the value of the integral. And that means it converges. All right, it's important to notice that this doesn't really matter. I mean, I don't want to scratch it out. It's right, and it's equal to the area of the integral, but I was asked about a series. So all that really matters is that I found out that it converges, and then I can say by the integral test, the series also converges. But I said this number wasn't important, and the reason I say that is because I don't want you to think that the series equals this value. This is the value of the integral. All right, not the series. The series converges, but it might converge to a different number because of that whole finite difference thing. So let's take a look at an example that shows why they might be different. Something a little bit easier than this one. All right. So here we have a series and an integral. They both start at the same number, 1. They're both going out to infinity, but here we have the series and here we have the improper integral, and we should be able to show that those have different values. So the way I'll go about doing this is just computing the integral first, because it's easier to compute integrals usually. All right, so I'll start with the integral, 1 to infinity, x to the negative 3 dx. That'll probably be easier. And then that's going to be the limit as b goes to infinity, 1 to b, of x to the negative 3 dx. Increase the power by 1, divide by the new power, and then plug in top minus the bottom. See, x to the negative 2, that's the same as putting it on the bottom. And then plug in the bottom, minus the negative 1/2 over 1 times 1 squared. And what does that leave us with? All right, I've got negative 1/2, b to the negative 2 is b squared on the bottom, but that's going to infinity. We got a fraction that the denominator is limiting to infinity, so that vanishes to nothing. Over here on the right, what do I got? Negative, negative becomes positive, 1 over 2. Okay, so there's the value of the integral. Okay, what about the series? All right, well, n equals 1 to infinity, 1 over n cubed. Let's just start writing out terms. That's going to be 1 over 1 plus 1 over 2 cubed is 8. 3 cubed is 27. I don't want to do any more than that because all I want to point out is that, well, shoot, that's bigger than 1 over 1, which is 1, and that's bigger than 1/2. And 1/2 is the value of the integral from 1 to infinity of 1 over x cubed dx. So that finishes the proof right there because I've shown that the series is not only not equal to it, it's actually strictly bigger than the integral. If that makes sense. They're both finite. This number, whatever it is, it's finite by the integral test. but it's different. It's a different finite number than 1/2, which is what we got from the integral test. It has to be at least as big as 1. It's bigger than 1 plus 1/8, in fact.